Okay, so our math now was all about solving, and it was solving linear and quadratic equations. And again, to really put it to words, it's inverse operations. Quadratics have more than one solution by bifurcation. We're getting all the variables on one side, and we might have to simplify. The reason why we need to know this stuff is that we are shifting into solving. Where's my little mouse? We're shifting into solving exponential and logarithmic equations. Okay? There are, like, you can argue that there are many layers or many levels of this type of stuff. Today we're just starting with the most basic version of solving exponential and logarithmic equations. They're going to look like this. I know, looks kind of gross, right? Because it's an exponential equation. It's got variables in the exponent. If it's a log one, it might look like that. Log base 3 of 5 minus 2x equals log base 3 of 3x plus 1. Yeah, looks kind of gross, right? The nice thing is there is a singular property that we can use to solve these kinds of equations. Now the property has a verbal version, like a written out English version, and then it has a math version, and the math version is really nice. This is the singular property that we would use. So I'll read what it says, and then you probably can just write down the property itself. If two powers have the same base and are equal, the exponents must also be equal. And so what this property says, I'll write it over here so we can see it really big. What this property says is simply a to the power of x equals a to the power of y. If that's true, it must also be true that x equals y. Kind of makes sense, right? If I have the same base raised to a power and those things are equal, the powers themselves must be equal. So in this case, how could we simplify this equation? What could we do to this equation to make it easier to solve? If it's 7 to the power of 3x plus 2 equals 7 to the power of 2x minus 1, what's the simpler version of this equation that we would solve? 3x plus 2 equals 2x minus 1. If we solve this equation and we find the values of x, because we're using this property, it should be the solution for the original equation as well. Oh, this looks just like the math now, right? We have x's, they're on both sides. What should we probably start by doing to solve this? 3x plus 2 equals 2x minus 1. What would be the reasonable first step to take to solve this? Subtract 2x from both sides. We want to cancel out our x variable on one of the sides of the equations. So this cancels out here. What's 3x minus 2x? X. X plus 2 equals negative 1. Oh, we subtract 2 from both sides. X equals negative 3. How do we test to make sure that what we did was correct? We would plug it in. Now, theoretically, you really should be going back to the original equation, right? We're going to find some cases where we're going to find solutions, and if you don't go back to the original equation, you will not find out it is a solution or not. We're going to build up to that. For right now, I think it is, unless I made some mistakes today. Maybe I did. But that's kind of the idea of what we're doing, okay? So let's go back to the original equation and let's plug in negative 3 and see what we get. So we would get 7 to the power of 3 times negative 3 plus 2 equals 7 to the power of 2 times negative 3 minus 1. And then we would straight up plug those two expressions into the calculator. If you want to simplify, you could. You end up getting negative 7 as the power and negative 7 as the power. So we can probably assume that 7 to the negative 7 and 7 to the negative 7 are the same thing. But you gotta go back to the original equation. Can I get a quick 3, 2, 1 on using this property for exponents? Okay, Aaron, you held up 1, and then 3, and then 3. You got it. Tricked me. Okay. It is almost the exact same thing if we're working with logs, right? Notice that the language of this statement is pretty much the same. If two logs have the same base and are equal, the arguments must also be equal. What do we mean by arguments? What is the argument of a log? What is the argument of a log? Yeah, the thing that you are taking the log of. So just as a reminder, argument is this whole thing inside the parentheses. Do we have two logs that have the same base here? Yeah, that means that we can just say that the arguments are equal. So we can simplify this equation to be 5 minus 2x equals 3x plus 1. And then we would just solve this using normal inverse operations. How would we solve this equation? What's a reasonable first step? You could do minus 3x. My preference in this case would be to not end up with negative coefficients for my variables. So what would my first step be? I would add 2x to both sides. I think becoming comfortable with working with variables on either side of the equation will help you out in the long run more than always having your focusing on your exponent. Also, can you just switch the two sides of this equation right now? Yeah, anytime you want, you can just switch sides of the equation. Right? What's our next step to solve this? What's that? Subtract 1 on both sides. Right? So 4 equals 5x. And then we would divide by 5. And that would be x equals 0.8. X equals 0.8. Did I make a mistake, Ava? Okay. Okay, how do we check to see if this is the correct solution? What do we plug into and which is the original equation in this case? The log base 3 one. You have to go back to the original equation. Okay? So I take my 0.8, I go back to the original equation, I literally plug in 0.8 in place of x. And I check to see if I made any mistakes. And I would grab the calculator and I would do log base 3 of this entire expression and log base 3 of that entire expression, and I should be getting the same value. Okay? Everyone needs a calculator today, so take 20 seconds. Go grab calculators. 1 person per group, 2 people per group, whatever. And then check that that works. Yeah.
Thank you very much.
Because I didn't want to have negative quotations. Okay? Plug it in. Log base 3. Remember log base is under the math button. Aaron, quit trolling Beto. Right? Log base 3, you put that in, you should get some number that is a little bit more than 1. You should get the same thing on both sides. Did it work? I don't know. I didn't mess up. So, hopefully you're getting the same value. This property is actually really simple to use, because you just have the same base and then you just take the value of the exponent and make it that. The part that makes it challenging is that you might be given equations that are not simple enough to do this to. Here is an example of an equation that you cannot just immediately do this property. Why can't you immediately use the property that we just explored to solve this equation?
Because there isn't an argument on the right side.
No, there is. Sorry, that's my bad. I should have put parentheses around that. There's an argument right here. That's the argument. Well, I want to be careful about saying solve. Yeah. What's the real problem? There are multiple logs on the left side. We can only use this property if it's log of an argument equals log of an argument. This is why we study the log properties. This is why you learn the difference of logs and the sum of logs and all that stuff. It's so that we can manipulate these to solve equations like this. So what do we have to do to solve this equation? We have log of 3x minus 2 minus log of x plus 1 equals log of 2. How do we turn the left side to only have one log? Does anyone remember what subtracting 2 logs becomes inside the argument? It becomes division. So the left side would simplify to be log of 3x minus 2 over x plus 1 equals log of 2. Do you remember that? Spent 2 days on the properties of logs, right? Okay? So these are the properties of logs. And we might need to simplify one side of the equation before we're able to use the property that we saw at the start of the lesson. But now, do we have 2 logs that are equal to each other with the same base? Is log of this side, log of that side, do we have the same base in this case? As a reminder, what's the base if no number is written? 10. So we can use our property, and this just becomes 3x minus 2 over x plus 1 equals 2. Oh, that's a rational equation. We spent a week solving those before. Oh, we start by multiplying by x plus 1 on both sides, right? That cancels out here. 3x minus 2 equals 2x plus 2. And now we're just solving using the normal processes of solving learned about numerous times. I believe if you solve this equation correctly, you end up getting x equals 4. I believe. Right? Boom, boom, x equals 4. What do we now have to do? You have to go back to your original log and check it. So we go back up here to our original log, and we substitute in place of x 4. And then we plug this side of the equation into the calculator. You could simplify it by hand if you want, but I think unless you're not allowed to, you check it in the calculator. Right? So everyone grab your calculator, check the left side of the equation in the calculator, see what you get. Check the right side and see what you get. Does it work? Carefully, the negatives and works. Yeah, it works. Okay. I know you don't want to. It is a requirement to check every solution to every log equation that you solve. We're going to see on Friday why. Okay. Last example. Why can we not use our if 2 powers have the same base property in this case? can we not use, if two powers have the same base, then you can set the exponents equal to each other, in the case that we have right here? Not a trick question. They're not the same base. You can only use this property if you have the same base. So at a first glance, I have no idea how to solve this. The question you should ask yourself is, can I modify one of these two numbers to be the same base as the other one? This is where having a little bit of knowledge of common powers of small bases is helpful. Is 27 a power of 3? You can check if you want. Grab your calculator and do 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, and see what you get.
Is it not 3 cubed?
I think it is, but we want to confirm. It works, Jersey? So, here's what we can do. We can modify one of the two sides to have the same base as the other side. So this stays as 3 to the power of 5x minus 1, and it's going to equal, as Lexi said, 3 to the power of 3 to the x plus 2. Oh, we learned about the properties of powers as well. If you have the power of a power, what do you do with these two values to simplify it? Anyone remember? What does power outside the base, or outside the exponent, become inside the exponent? What was that, Beta? It becomes multiplication. So this right side would simplify now to be 3 to the power of 3x plus 6. And if you look now, we have two powers that have the exact same base, and we set the exponents equal, and we solve. In the interest of time, I'm not going to do it, just because it's solving linear equations, which we can all do really well. I believe you end up getting 3.5. You go back to the original equation, you plug in 3.5, you make sure it works. Okay? So, to really put like a cap on all this, we're just using this singular property. If two powers have the same base, you can set the exponents equal to each other. If two logs have the same base, you can set the arguments equal to each other. And a lot of what our work is doing is modifying equations so that we have the same base on both sides. Can I get a 3, 2, 1 on like trying on how ready you are to practice this on your own? 3, 2, 1 on your level of readiness to practice. Okay, so we're going to practice. We're going to pass out some practice. This will be checked. I'm only checking it because I think that everyone's capable of doing it, right? Actually, I don't know. Should we check this, or should I just post solutions so that you can practice? Anyone have a preference? Angelica? Okay, we'll make it checked. I don't want to like give something that's too hard to be checked, but we'll check this. So this will be checked. Okay? You can work on it together right now in class. I recommend talking through stuff. We have multiple examples. Oh, I gotta stop the video. They're gonna complain.
Well, that's only 2.